Hello. For Unit 5, we're going to look at something called dimensional reduction. We're going to get into higher dimensional data now, and we're going to look at how at least some ways of handling it. And one of these is dimensional reduction. So if we have 1,000 different dimensions, reducing it down to maybe a dozen dimensions so we can process it better in our data. So let's start here. Look at our data, our Unit 5. There's a couple of resources here, including this video, which will be posted here. So for a quick overview of one way of doing dimensional reduction, we're going to look at principal component analysis. This is one of the most common ways of doing dimensional reduction. And there's some really good explanations out there on the internet for people. So the first thing I recommend is everyone go look at this overview of it from the University of North Carolina at Chapel Hill.
Stat. Quest.
So this video is from an instructor who also is a musician, so he plays his own intro with the banjo. So anytime you can have a banjo playing professor, I think that's good. And then it goes over this principal component analysis and talks about that. It has a nice application to biology using blood cells, which is a cool application. So now it gets the first 12 minutes are quite good. Then it gets some more details that we don't necessarily need. So you can watch the whole thing if you want, but certainly I suggest you watch the first 12 minutes of it. Now, if you have a little bit more math background, or at least you don't mind mathematical terms, the Georgia Tech version that's posted to the DASD free course is quite good. But it's going to be using terms like eigenvalue and orthogonal in that. If you have linear algebra background and want to really know what's going on here, the University of Washington has in their data for bio version this linear algebra dimensional reduction. This is actually a first of a three-part series, and so you can look at that. But again, I don't expect students to have much math background here, so these second two are certainly optional. But I want to just provide them to you because I know some of the students have had a math background here. Now there are some resources out there. We've been using this sklearn or scikit-learn resource or library out there, and it has some nice resources for this also. And a lot of this revolves around the iris flower data set that we've looked at before. So this is one that looks at this data set and tries to show a view of it and then how we can reduce it in 3 dimensions. We'll do something similar to this in the practice activity. Now we'll be looking at principal component analysis, but there's also another common way of doing reducing dimensions called linear discriminant analysis. Now, linear discriminant analysis has to be trained on data sets too and set up. And so this actually discusses and compares the two. But again, we're not going to go into it. We're just going to focus on PCA in this class. But I just want to mention linear discriminant analysis so you'll hear that at times. It is a simplified version that can be used for classifying data, but it also can be used for dimensional reduction. So it can be used for both. And we'll be looking at the simple PCA, which kind of does some linear stuff. But there's also something called Kernel Pca. Sometimes if our data is clumped in different ways, normal PCA will not be able to handle this type of data and map it very well. And so there's something called Kernel Pca. And again, I just want to mention that if you get into complex data sets and things are not working well, there are a couple other ways of doing dimensional reduction. Last thing I want to look at is this article here on in-depth, goes a little more in-depth on this. And talks about this. So, I mean, the whole idea of principal component analysis that you see in the video, and you'll see the same thing here, is that we can take two-dimensional data and map it onto one dimension here, or 2 dimensions and stuff like this. So this walk you through, but again, the videos will walk you through this practically this exact same example here for us. So I'm not going to go over this. I suggest you watch that. But now this talks about handwritten digits and using PCA for that. And we will be loading this handwritten data set here and working with that. This handwritten data set is called MINST, M-N-I-S-T. It's a really common data set for beginning machine learning. And this is a sample. Each image is one digit that's handwritten. It's kind of from a zip code sort of idea. And there's lots of different examples of that. And this data is 64 by 16 by 16 pixels. Here are some zoomed in versions of these, so you can kind of see the pixels, 16 by 16 pixels. So that means there's 64 pixels in each image. So that gives us 64 features that we have to look at and categorize. And so it's really hard to kind of analyze that. Now 64 isn't too bad, as we'll see. We can easily actually do that with like support vector machines and stuff like that. But if these were larger images, let's say 1,000 by 1,000 or something, so we're up in the megapixels, then PCA gets even more useful here. So here we're just changing the 64 dimensions down to 2 dimensions and and plotting them, and you can actually see that it does a pretty good job at mapping out so that all the numbers that are 0 or all the numbers that are 3 and stuff clump together with only 2 components. So again, we've taken 64 features and mapped them down to just 2 components here. And we'll see in our practice activity how we can do this in our Python code for that. For this. Now I'm going to, in the lecture, in the practice activity, I'm also going to have you look at some things where you'll see as the number of components shrink, the amount of information we have shrinks also. And so there's usually some sweet spot in here where we can reduce the number of components significantly without dropping off our accuracy for prediction a lot. So a lot of times when we're doing principal component analysis, we want to try to reduce the number of components like this from 64 down to some value, maybe like around 10, where we still get relatively accurate information, but we've reduced the number of features, the size of our data set by about a sixth for that or more. So this is where I'll have you read this PCA noise filtering, and so I won't go over that. I'll have you read what that's doing. But I want to talk a little bit about another version of PCA called eigenfaces. What was done previously was that people have taken faces and applied principal component analysis to them, and that generates some feature sets that are interesting. And what it tries to do is extract some useful features from different faces and what's useful. So what this does is try to show, looking at different faces, what are some of the common features. So and this is the first principal component with the most information. It goes down here by the things, and you can kind of see the first thing it just kind of looks at is the general face outline, and sometimes the face is shaded here and looks at, so it's going to look for a circle here. The white is kind of what it's focused on, so it's either focusing on the edges where there aren't a face or the middle where there is face. And then it starts focusing on things like the eyes or just some general features with the head, or again this spot underneath right by the nose that outlines the nose and the mouth and things like that. But what principal component analysis was able to do is take face with many components, over 150 components, and reduce them to just a handful of components while predicting accuracy. And that allows systems to do face comparison. So when you're comparing one face to the other, rather than having to compare like 100 or 1,000 different features, we can just compare a dozen features and get a good estimate of each face for that. Okay, that's a quick overview of principal component analysis. Next thing I want you to do is go to this practice activity and work through that.